Hello everyone, my name is Igor Titov and I'm from the Kiel University. I am from the chair of Integrated Systems and Photonics, and today I would like to present our new results. And at this point I would like to thank the conference organizers for giving us this opportunity.
So my talk today is about refractive index measurement with a flexible OLED-OPD detection unit. Let's start with the fact that the refractive index has a large number of applications. It is mostly applied to identify a particular substance, confirm its purity, or measure its concentration. For example, in the food industry, we determine concentration of water in honey, and in the pharmaceutical industry, it is also useful for determination of drug concentration. And of course, one of the important applications is the medical sensing and diagnostics. So, for example, the biological tissue or whole blood can reflect the physiological state and plays an important role in diagnostics. In the recent years, researchers found several useful and really interesting applications by integrating organic optoelectronic devices to biosensing platforms to monitor blood flow and tissue oxygenation. Mr. Köpke and co-workers showed OLED-OPD arrays on laminated ultra-flexible foils with one type of optoelectronic device on each foil. They measured the oxygen concentration of blood when laminated directly on skin. Mr. Ken and co-workers presented the reflectance oximeter array in 2018. The OPD and OLEDs are fabricated on separate substrates and then assembled together. An also really interesting approach was presented from Mr. Lee. He and his co-workers presented a monolithically integrated ultra-low power OLED-OPD pulse oximeter. We also show our already in April this year published results on monolithic integrated OLED-OPD matrix geometry on a PET foil. As you can see, the device is flexible due to the 200 micrometer thin PET substrate, which was integrated with a PDMS chamber for sensing and fluidic applications. The system has a great potential for miniaturization and serves as a platform for several measurement approaches like sensing with reference signals or the redundancy approach. For further investigations, we continued our work with the array design, which I would like to present today. Our main purpose is the development of a monolithic integrated flexible OLED-OPD device for sensing in multi-analyte microfluidic applications such as whole blood, plasma, serum, or other fluids. We fabricated 6 OLEDs and 6 OPDs as an array, which 1 square millimeter devices are galvanically separated from each other. We sticked a PDMS chamber on top of the sensing platform to support the analyte transport. One of the great advantages of this work by integrating the organic devices monolithically is the alignment of the devices. Due to the use of shadow masks and the thermal evaporation technique, the fabrication of the OLED-OPD devices is quite simple, and that holds a great potential to fabricate the devices compact, miniaturized, and with a low alignment deviation, what results in a high reproducibility of the samples. These devices can be used for monitoring of multiple analytes by operating the pixels separately or in groups, and be used as reference signals or for the redundancy approach. As a small outline, I would like to present in the following work the results on monolithic integrated OLED-OPD devices for fluidic applications. We fabricated our devices for comparison with different organic materials, different geometries, and on different substrates. We conducted our investigations with an experimental proof of the refractive index sensing mechanism. Before I go further to the experimental details, I would like to show the schematic of the used system. The refractive index sensing mechanism is based on the light intensity changes on the OPD, which is emitted from the OLED with a Lambertian emission pattern, which is shown in the graphic. As you can see, a part of the light remains due to the total internal reflection in the substrate as a guided mode, and the other part enters the analyte inside the PDMS chamber. As the total internal reflection condition is a function of the refractive index of the surrounding medium, the detected photocurrent depends on the liquid inside the PDMS chamber. We expect a stronger reflection on the OPD or on total OPD for low refractive index fluids and less light on the OPD for a high refractive index medium, and consequently higher photocurrent on the OPD for a lower analyte refractive index. As a combination of organic devices, we use different types of organic material stacks. The desired high precision patterning of the OLEDs and OPDs were achieved by using shadow mass during the thermal evaporation process and the photolithographic process of the ITO node. The organic devices itself were evaporated step by step by using different shadow mass for the OLED, the OPD, and the aluminum cathode. In explanation, I will just focus on the active materials. The OLED-OPD unit, which is shown on the left, was fabricated on a 25 to 25 mm glass substrate with a thickness of 1 mm. The OLED is based on a green emitting phosphorescent iridium dopant, and TCTA is a host for the electron emitting layer. Green emitting sources are often used in PPG systems for blood absorption measurements. On the other side, we use copper phthalocyanine as an active layer for the OPD and C60 to fabricate the donor acceptor system. Further, we use lithium fluoride and aluminum as a reflective cathode and indium tin oxide as a semi-transparent electrode, which makes the OLED bottom emitting. And due to the great advantage of the design freedom based on the organic devices, we design different geometries of the evaporated systems. Here we show a coaxial shaped OLED-OPD design with a round OPD and a surrounding green emitting OLED. To investigate the impact on its refractive index sensing mechanism with fluids, we conducted the investigations with refractive index measurements to present the experimental evidence. For this purpose, we carefully prepared glycerin water solutions of defined values described in % by weight. The fluids were pumped alternately with a syringe through a PDMS chamber. On the right-hand side, we show a measurement of the visualized sample. As you can see, we pumped first 5, then 7, 10, and 15 glycerin water solutions in % by weight to show a staircase-shaped change of the refractive index inside the PDMS chamber. A higher glycerin concentration causes an increasing of the refractive index, and as I already mentioned, the photocurrent decreases for higher refractive index, which can clearly be observed in the shown measurement. The LOD was calculated to be roughly 4.8 times 10 to the power of -4 refractive index units. And as a conclusion, the increase of the reflective index of the fluid was clearly observed, but we also see a degrading effect of the OLED. And this is a well-known effect actually, and can be accelerated by poor encapsulation of the organic stack due to water and oxygen impact. Further, we fabricated 4 OLED-OPD units on one single substrate. We investigated the integrated optical platform by performing a very similar measurement like with a coaxial designed OLED-OPD. To increase the visibility of the refractive index changes, we injected water between the glycerin water solutions. The fluids with different refractive index values can clearly be distinguished. We injected again 5, 7, 10, and 15 glycerin water solutions by weight with normal tap water in between. It can be clearly observed that the photocurrent decreases for a higher refractive index inside the PDMS chamber. The LOD was calculated to be roughly 3.2 times 10 in the power -4. This approach allows us detection of multiple fluids at the same time and integrate reference signals or use the triple modular redundancy approach to get a system which processes a single result by majority voting of 3 inputs. If one input fails due to inhomogeneities like bubbles inside the microfluidic chamber, the other 2 inputs can correct the error. For the following devices, we use a deep blue light emitting organic materials for OLEDs. The blue emitting fluorescent dopant is BCZ-VBI in a DP-VBI host. On the OPD side again, we fabricated the same donor acceptor system but used BFEN as an electron transport layer instead of TPBI. We also used this blue emitting OLED in our experiments for a flexible OLED-OPD matrix unit for fluorescence measurements, since there are several quenchable fluorophores like the ruthenium complexes which are absorbing blue light. Here we use again the coaxial shaped OLED-OPD design fabricated on a glass substrate. The experiments were figured out in the same way like before and show also really promising results for refractive index sensing with fluids. We injected 4 and 8% glycerin water solutions by weight with normal water samples in between. The switching behavior of the refractive index change can clearly be observed. Afterwards, we calculated the limit of detection to be like 3.2 times 10 in the power of -4, and the OLED-OPD show a very comparable behavior like the green emitting devices. However, these devices represent the heterogeneous monolithic integrated OLED-OPD systems, but since they are evaporated on glass substrates, they are of course not really flexible. So let's make a step towards the integration of organic materials on foil. For this proof of concept, we used the array design which I showed up at the beginning of the talk. We fabricated 6 OLEDs and 6 OPDs as an array for parallel sensing of analytes. The focus of the design is to avoid electrical connection of OLEDs and OPDs, since the matrix design we already published showed up issues with leakage currents between the devices. For further investigations of the geometry, we placed a PDMS chamber on top of the flexible 200 micrometer thick PET foil with evaporated OLED-OPD array. To show the refractive index sensing ability, we injected now tap water to fill the chamber or just air to decrease the refractive index inside the system significantly. The switching behavior of alternately changing refractive index inside the fluidic chamber can clearly be observed. The limit of detection was calculated to be 6.2 times 10 in the power of -1 and is obviously not on the level as the previous presented samples yet. So overall, we demonstrated a successful proof of concept by presenting the switching behavior of the OPD signal by changing the content inside the PDMS chamber. This proposed monolithic integration of devices demonstrated to work. The low LOD is due to the small device sizes and currently not well adjusted gaps between the OLEDs and the OPDs. Now I would like to give a short summary and a small conclusion of my talk. The presented research demonstrates that the integration of a flexible OLED-OPD unit with 6 OLED-OPD pairs and a flexible PDMS microfluidic chamber can be used as a measurement system for refractive index determination of fluids. We conducted this proof of concept by subsequent filling of the chamber to achieve refractive index change. We obtained a limit of detection of 3.2 times 10 in the power of -4 refractive index units for glass substrates and an LOD of 6.2 times 10 in the power of -1 for thin flexible substrates. This system holds great promise for a highly flexible and lightweight refractive index measurement unit. The heterogeneous integration of OLEDs and OPDs on one single and preferable flexible substrate has a great potential for optical sensors with high precision alignment of the devices and serves as a platform for the research, medical and other several industrial applications like improving the drug development process or monitoring of important diagnostic patient informations. At this point, I would like to acknowledge my colleagues from the Chair of Integrated Systems and Photonics, thank for the financial support of the below listed projects, and of course, thank you all for the attention and wish further on a nice conference. Bye bye.